Hello YouTube, and welcome to the third in the series of the Impl MeatPack crate, where I've just been given a run through of how I've created the MeatPack crate, potentially for future me and for yourselves to understand how you might want to use it, but for me also to maintain it going forward. I can remember why I built it the way I did. In this episode we'll be looking at Unpacker, how we then can accept some MeatPack code and how we process that and then create the original G code that it came from. So what I did was create a new module in components called Unpacker, and in here is going to be our Unpacker struct. Like I say, that's going to be the struct that's going to unpack our meatpacked G code. In it, it's going to be very similar to Packer, where we're going to have a user-defined use size for a inner buffer that we're going to unpack meatpacked G code into, and that can be defined because we want it to be used for no stud and stud environments, so we can't allocate it if we want to avoid using an allocator. If we want to just use no alloc in our no stud environments. So the user has to predefine that for us. So in here we put a const s usize, which is going to define that usize for the inner buffer. So the unpacker for us is going to have a state, because as we unpack the G code, meatpack G code, there will be certain states where we'll be waiting for a full width byte. When some of the characters do not fit into the 15 character subset of that we represent by U4s, we have a flag to say there's a full width byte on the way. But also we have states where we've got that minimal kind of control plane to say whether meatpack is activated or not. And so if it's not activated, we might just want to continue just passing those bytes through. When it's activated, of course, then we want to unpack those using the meatpack algorithm. So I'm going to have a state, and we're going to call it meatpack state, and I will define that in 2 seconds. Also got a variable called no spaces. So of course the algorithm has kind of two states where you can either factor in spaces, and that is included in the packing algorithm, or we discount spaces because we may have already removed them. So then we can exchange that for another character. I believe if I go back to the meat, we exchange it for E. So when spaces are available, or we want to pack spaces, we can include them in the part of the 15 characters. If it's not included, then we use E instead to pack that. So we'll put that as a flag to say whether we need to include those or not in the algorithm. We'll have a flag for clearing the inner buffer, so very similar to how we did in the Packer struct. We've got this internal buffer. We're going to then reveal part of it once it's filled out with the line of G code, that the corresponding line of G code for the meatpacked code, and then once that's been given out and handled and used by the user, we'll cycle back through, and then we want to clear that buffer and then start filling out the inner buffer again with new unpacked code. So we've got clear inner, and that's a bool, and then we've got a position, which is going to be the position in our inner buffer that we want to keep track of, and the inner itself. So it's just going to be an array of U8s, and it's going to be of size S. So that's our unpacker. We need to also actually add it to our module, so we need to do pub create mod unpacker, and then we'll get all our lovely syntax highlighting, and of course we're going to pub use expose this as our part of our API. Unpacker. So as it says, we've got this unpacker state that we need to define, and the unpacker can be identified in one of 6 states. So I'll create an enum for this, and then we call it unpacker state. And The first one is called first command byte that I have. So for the control layer, we were expecting to have 2 consecutive command bytes occurring. So this one is just to say that I've found the first one, so I'm now in state of first command byte. Now I'll use that to then identify whether I should be expecting a second command byte, and if so, what to do then. So the second one is second command byte. So I've reached the second command byte. Now I'm expecting the actual command byte itself, and then I'll need to action on that. Remember, whilst we're unpacking, we're going to be unpacking a byte at a time. So the user can just feed us single byte at a time, and we'll slowly unpack them until we've got a line of complete G-code to return to them. We also have a state of right full width byte and left full width byte, and these will become a bit more apparent as I go down and show how we unpack some of the G-code, because when we've meatpacked it before, we said there's either a flag, there could be a flag to say there's a full width byte coming along, and that could be positioned in the least or the most significant bit of the U8. So given where it is within that U8, it will tell us whether to append it or it needs to be inserted in the middle of the other byte that was in the other U4 that we want to unpack as a U8. So we want to put that before or after that U8. That's what we'll use that flag for in a minute. Then we have enable, enabled. So whether we are actually enabled, so we're in meat unpacking mode, or we're disabled and we're just going to pass the bytes through. So it's all right, it's going to stream it at the moment because we haven't used any of these fields, but we will in a moment. So the first thing we want to do is impl the unpacker. So SU size default. So I've got my default state. So this is a and again we'll just say S. So yeah, this is just implementing the default trait for Unpacker. So we need to then create the function default and return. We're going to return self, and it's going to have a state of Unpacker state disabled. So we're always going to start off in this disabled state. Hopefully, as we pass the MeatPack G-code through, we'll find the control signal to say, let's start unpacking the G-code. We will default to this no spaces as being false. Clear inner, of course, it's going to be false because we haven't unpacked any G-code. Our position is going to be 0 in the buffer, and we need to initialize that inner buffer as well. So it's going to be those U8 of size S. Okay, and there we go. That helps with all those hints. Oh yeah, it's not that. It's also of null. Yeah, 0 bytes. Okay, so that's our default implementation. And now, yeah, like you said, we still got all these errors that we haven't used these variables just yet, but we will do 2 seconds. So that's our import for default. And now we can implement for size. We're going to implement the unpack function here. This is going to be our functions that are attached to Unpacker. So Unpacker S. And the function that we have for unpacking G-code is called the unpack. Well, we want to publish it first. Pub fn unpack. And the unpack function is going to accept a mutable self because we can update our own self in the unpack struct, and we are going to accept a reference to a byte that the user has received either through some kind of serial port connection or from an SD card or some kind of IO processing. And what we're going to return is a result, and we're going to do the MeatPack result again. So this is the are we waiting for more bytes, or have we got a line to give back to the user? And we also potentially could raise an error whilst we're unpacking our G-code, and we'll raise that to the user as well. So that's how, like you say, the unpack function. Oh, whoops. There we go, curly brace. Open curly brace there. That's a bit better. And I'll just put to do here. So, okay, so now we get into the how we're going to get. We've got this byte coming to us. How do we start unpacking? So the first step of it is going to be similar to Packer. We want to check if we are wanting to clear the inner, because we've released a line in a previous iteration, previous stunts. So we want to do self.clear inner, and we're going to define that function now. So clear inner is going to be very much the same as we had in the Packer. So fn clear inner is going to have mutable self. It's going to return nothing, and what we're going to do is self dot self.inner dot fill the entire buffer back to 0 to reset it. We're going to say self.position is going to be back to 0, and we're going to then clear the flag so we can activate that again at another time. So we'll set that to false, and that's our clear inner function there. Right, so we've passed that stage where we just start checking if we need to clear, and now we want to do our first check of what is this byte that we've received. And the first one is to say, is it a one of those control plane bytes? So I created a function. You've got a function called is. I've got it signal byte in the actual thing, so let's call that is signal byte. So indicating that there's some kind of control or command on its way. Put it in there as byte, and that function is. I'll just double check where it is. There we go. Okay, so I will create it. I think I originally had it in Meat, so we can place it back in Meat here as well, so you know where it is in the code rather than having to in the actual code. Let's scan to the bottom. So yeah, I just had it's just a little function here just to say, is it a signal byte that we're interested in? I'll just put a bit of like semantics around it. So is signal byte, it's going to accept a reference to a U8, and it's going to return a bool, and what it does is look for matches. It just matches on the byte, whether it is 255, which is the one to indicate it's a match. So that's how it is signal byte. So if I retype this, we can import it into our Unpacker. And I go now back to my reference. What we want to do here is then, like say, match on our state. So given this signal byte, now what do we expect to see next? And what we expect to see, if we're in the state of Unpacker first command byte, so we've already seen one, then we just want to process this one and say, yep, we are in the state of the second command byte. So we will expect to see the command coming next. So we can then return OK, and the MeatPack result here is waiting for next byte. The other state that we may be in is that we're in disabled mode. And therefore then this might be our first command byte that we've come across. So we want to say, we're in disabled mode, this command that's incoming may be going to tell us that we are going to enable MeatPack, and then we can return OK MeatPack result, waiting for next byte. The other one is that we are actually enabled. Oops. So we are currently processing MeatPack's G-code, and we are now hit the first command byte. So we'll just set we're into the first command byte mode. Then we can return OK MeatPack result, waiting for next byte there as well. Okay, and then for everything else, we shouldn't ever be in another state and expecting another command byte. We shouldn't be in the second command byte and receiving another one. We shouldn't be looking for a right full width byte or left full width byte and it to be a command byte. So in those states, we want to, I've got it to reset itself. So self.position, self.inner.fill with zeros, just, you know, empty out the entire struct, and then actually we'll return an error, MeatPack error, and I need to define this one. So if I just put MeatPack error there first, we go into meat where we've defined our errors. Here we wanted to find an error called invalid state. So yeah, I'm just adding the semantics, invalid state, and the enum is just, as you could imagine, invalid state. So then I can, now I've created that, we can add it to our, you know, our logic here. So signal byte comes in, we either haven't seen one before, so we're in first command byte mode. If we're in disabled, we also go to first command byte mode. But if we're in first command byte mode, we go to second command byte mode. If we're enabled, we go to first command byte mode. If any other ones, we shouldn't expect to receive first a command byte. Therefore, we will exit there with an error state. So now we want to match against self.state. So let's say it isn't a command byte, so we'll continue on. And of course, the first one of the states that we could be is in disabled mode. And here we just want to return the byte as if it's return the byte, but actually just append the byte to the inner buffer, as we don't need to operate on it at all. So we just need to do push this inner buffer. The push is the same function as we had in Packer, so I will go grab that for ourselves. Just go down here. I'll copy it and paste and bring that over. So again, the push function here is just going to check whether we are in a state where we've overflown the inner buffer, and then we'll error with a buffer full. If not, we will then just append the byte and increment our position along the buffer. So that's all added there. Oh, and I just need to borrow the byte there. Unpacker disabled. Oh, sorry, unpacker state. That's where it is. Here we go. Oh, this should be okay now. Oh, whoops, I need to dereference it. There we go. So yeah, just dereference the byte, so it can be appended. Now we need to handle, like you say, the non-exhaustive pattern here. We need to add some more patterns to look for. Well, actually, the one other thing we need to double check is that we've added to the buffer, but let's just double check that if the byte, if we dereference that byte again, is equal to a new line byte. And if so, then we will activate our inner to say we want to clear the buffer when we go next time we go round the loop. But at this stage we want to then say meatpack result. We've got a line for the G-code line for the user, and we want to pass that line. And this was going to use our self.return slice, which again is the same functionality as we had in Packer. So if I bring that in, okay, and that's all this is doing, is just giving the slice that we need of our entire buffer. We don't return the entire buffer, we just go to the end where the data is present and return that to the user. So that keeps it, like I say, just nice and usable for them. I could actually, with this push, clear in and return slice, we could actually probably make that as a separate trait and just use those on both Packer and Unpacker, because they have a buffer to use. Maybe I'll look at that to simplify the code rather than duplicating code in the future. So it's just giving me some warnings here because we haven't completed the options here. So what the other option is okay, meatpack result, result waiting for next byte. Okay, so those are the options. Mismatch return, so that should be okay once we have this is like just happened just like we had before. I need to add all the states in, and we can then look to hopefully it'll clean up the errors as we go. Or more so the warnings. So we've got the other state of enabled. If I just here we go. Let's try and put these all out, and then we can fill them in a second. So I'll just say waiting for the next byte. I just copy and paste this across a couple of times. So we have enabled. We have first command byte, second command byte, right full width, and left full width. So let's put all our options in there. So there we go. So that cleans up all those like warnings, just to say that we haven't completed the exhaustive check. And at the moment we're just defaulting to returning OK bytes, but we need to actually put in the logic now. Right. So the next one there is Unpacker enabled. So we actually need to do apply our algorithm. And this is actually really not too much trouble at all, because we've got our we're going to take get the byte for the that's U4 in the most significant byte bit of the byte, and the least significant bit of the byte. So most and least. We're going to do byte.unpack, and we're going to give it. And we need to give it the control whether it's spaces, whether spaces are enabled. So this, if we remember back into the first episode, we created the unpack function, which is actually just this these forward lookup and reverse lookups, and the unpack function takes a U8, does some bit manipulation to shift the bytes to get the most significant and least significant 4 bits, does the reverse lookup on each of those to get us our U8 variant, which is the unpacked version, and we pass that back. And we also created a trait on U8 here, implemented on the U8 called pack, which gives us the unpack function and makes it available to any of the U8s that we import that trait at the top level. So we've imported pack at the top level, so then any U8s that are present in this part of the code, we can use the unpack function. We also need to question mark that to return types. Be okay. Let's have just double check my. So unpack returns just 2 U8, so that's okay. That's okay. It's because I've removed these. Okay, so if I take this, there we go. There we are. It's just saying we haven't returned at the end of that statement yet, but we still need to fix this logic up here. So what we need to do now is match on these two U8s to say, okay, what is the most and least bit? What do they look like? So one of the options is that we returned 2 new lines. So if we got to a stage, and if you look back on in the packer, that we ended up having a full packed line of code and we've just got this one floating as a like new line character, we just pack it with another new line and then continue on our way. So when we unpack, if we see 2 new line characters, we can or line feeds, we can just take one, and then we don't have to like have that extra padding being introduced into the G code. So we can just do self.push the new line byte. The other case that we could have is that we have some kind of signal byte. Oh no, that's not, this is not the signal one. This is the full width character byte, and some other byte of one of the other 255 bytes bit. So here we just want to then self.push if it the least significant byte in, because so the one here is that it's going to be the least, so we want to push that into the buffer, and we want to self.state equals unpacker state. So now we want to say, look, we're going to expect a write full width byte, so this should be added on, and when we get that next byte, we'll have, and we've got the cases down here where we deal with, it's a right full width byte or it's a left full width byte. So we'll deal with that in one moment, but at the moment we just need to indicate that the next byte coming along is a full width byte. The other way is that says that we have a U4 that's being packed into U8, and we also have a flag to say that there is a left full width byte on its way. So we just need to that U8 there. So in this case, we want to push the most. We want to push the least. So this is where we'll see the trick occur in a bit here. So we want to push the least, and then we'll push the most. Oops. So we will keep the least in the buffer, and we're going to have to remember this at the next stage when we do the left full width byte, and when we go into that mode, is that actually we want to then flip that out. So we want to exchange that flag for the actual byte that it represents. Just need to state equals unpacker. So this is that state equals left full width byte. So this is that little trick there, just to save those few little U4s here and there, where depending on how you're packing, you may have this like remaining U4 ahead of you because you've got 2 full width bytes on the way. So you can then kind of try and use that U4 more efficiently and maximize the packing potential. So that's the least full width byte, and then we've got a case where we've got two signal bytes. So that's the fact that we've got 2 full width characters coming, but that's actually unreachable here because we should expect that represents a command. So we shouldn't get to the stage where we're entered into a state. So these 2 zeros will actually represent command byte, a signal byte up here. Therefore, we should have dealt with it up here. If not, we've got an issue. So we need to declare that it's unreachable here. The last bit is that we've got a most and a least. So we've just got two standard U4 representations that have turned into two U8 representations, and it's just a case of just appending those, push those to our buffer. So push most. So yeah, least first, most next. So, and of course we need to unwrap those and promote, progress those errors if need be. Right. So that's all our checks on what combination of U8s that we've received. Then we can match on self.state. And this is just checking whether we need to checking whether we're in an enabled state or a any other state, and check whether we've received a new line and we want to return that. So if we're in the enabled state, and if self.inner, I'll do self.position -1 is equal to a new line. So we're just checking again whether we've added a new line to our buffer, and self.position is greater than 1. So here what I was saying is we could have checked, we've added new lines here and we might have added a new line here, but yeah, and then returned earlier on. I thought just add those to the buffer, do the check in one stage, one point in the code, and we're also checking whether the buffer is of length greater than 1, so there's actually some content for the user. If not, we might as well just ignore it because there's nothing usable for them. So if that's all well and good, we can then say highlight to the struct to clear the buffer in the next trip round, and we want to then return return OK, meatpack result line, and of course self.return slice that we created. So that's okay, because we haven't been exhaustive in all of our options, and actually that's the only option we really need to deal with, because we shouldn't be the other ones. We were expecting something else in the next round. It's only in enabled mode we need to handle potentially returning a line at the stage. So the other option here is if self.inner self.position -1 is equal to a new line, self.clear inner equals true. So what I'm saying here is actually, given that we're only interested in returning lines of some content, we're just checking this bit is just saying, okay, if I've still got a new line, therefore I'm only of length 1, I might as well just identify to clear the inner on the next loop round, so we ignore that empty line, and we can then just return meatpack results, waiting for next byte. Okay, so that's all well and good there. So that's just saying, because we haven't returned the line there, we're going to wait for the next byte to see what might happen. And in any other case, we'll be waiting for the next byte, be it that it's a full width character, we haven't reached a new line yet, we may be in the middle of some kind of command byte that we might need to handle as well. So that's should be good. And then we don't need that last one there. Okay. Meatpacker state, that's what we're looking for. There you go. So meatpacker state enabled, just checking for new lines. If it's all good, we either return the line or we wait for another byte. So the next stage is we're in first command byte stage. So we want to evaluate what this next byte is. So I've got a function here that we can define is like, let's determine equals determine command. And this is going to evaluate all the different commands that we may need to handle, and we need to provide it with the byte, but I need to define the function. So there's a number of bytes that are used for defining commands. So if we go to our meat and we can go down, we can add this function in. Got my reference. Okay, so this is also public const fn because it can be evaluated at compiler stage. So determine the command, and it's going to take a byte, and it's a reference to a U8. And it's either going to return a result of MeatPack command, or it's going to be MeatPack error. And if I do the enum here, so the MeatPack commands, and let's create those commands now, are okay. So we have the packing enabled and that command, the packing disabled command, reset all, query config, we have no spaces enabled and no spaces disabled, and then a signal byte. Again, this is the other another command byte for preceding one other. So this is just effectively a lookup that it takes the U8 representation of those commands and puts it into that enum form. So they are so we need to match the byte, and if it's a 246, it is an okay MeatPack command, no spaces disabled, and all of this is just in the the Python original Python library. It's just I've just ported this across, so if you're wondering where these numbers are coming from, one, I'm just referencing them from a package, but they were already predefined in the original Python package for MeatPack. MeatPack command, no spaces enabled. Then we have 248 is MeatPack command, query config, and we have 249, which is used for MeatPack command reset all. And in the current Rust crate, as I built it, we haven't used all the commands that are available to us, or haven't implemented them all yet. And that's a to-do on me or somebody else if you're keen to collaborate. So that's reset all, MeatPack command. This one is packing disabled, and 251 equals okay MeatPack command, I think it's packing enabled. And then we got the 255, which is our signal byte. And then anything else we should error, because we shouldn't be at the stage where we're evaluating a byte that's not the command. So we'll go back up to our error states here, and we'll create a new error, and it'll say invalid command byte received something. Let's see, and we will tell the user what this something is. So we'll say invalid command byte u8. Okay, so we'll pass that through, and then it will get populated by this error in our error string. So invalid command byte, just to add that here, and we will pass it, dereference the bytes that we received. So that's what that's for any byte to be. So anything else, any other byte. So that determines our command. So now we've got this function. I just need to import that into our unpacker. Just keep that from erroring for now. So we've got our command. We need to now work out what we need to do with it. Or it's going to propagate an error up through the stack for the API. Right, so we've got, just double checking, full width, unreachable, second command byte, first command byte. Sorry, this is actually second command byte. That's it, I've been working through there rather than first. So yeah, the second command byte, we know that this one that we've received should be a command. We check whether it is, and then I call the function that we'll define now called handle command. And we pass on that command. And then we just return, okay, waiting for next byte. So let's define that function here, handle command, cmd, it's going to be type of meatpack command, and it's going to be void. It's just going to, and it's a mutable self because we might have to update some of our internal settings. So we're going to match on the command, and we're going to say meatpack. If it's the packing enabled, we are going to say self dot state equals unpacker state enabled. Next one is meatpack packing disabled. We'll just do self dot state equals unpacker disabled. We then have meatpack command reset all. So the reset all gets us back into a disabled state. And it also sets no spaces to the default of false. Semicolon. We also then have meatpack query config, which at the moment I haven't implemented, but you can imagine just us creating some kind of struct or some string details the current configuration and reports that back to the user. Then we got meatpack no spaces enabled. So no space, self no spaces equals true. And we have self dot state equals unpacker state enabled. So yes, so when we see those spaces enabled, it also updates our state as being enabled. So it activates both actually. And then we have no spaces disabled and self dot no spaces equals false. self.state. But really, we should probably be in a state when we, when these are happening. We should be in the enabled state. And I think many of the times where you see it, I've seen it so far, is that you enable meatpack followed by a declaration of either no spaces or spaces, just to be clear whether we need to factor them or not. So those are those bits, and then we've got the last one, which is a signal byte. We don't do anything with that in this handle command stage. So that's our self.handle command function. So it's just taking those and updating our states, or various flags within the unpacker function. So that is the second byte, command byte scenario dealt with. Now we just need to deal with the first byte scenario. Just clean that up. There we go. And this one is a case of just saying that we are in in a state that we're waiting for unpacker first unpacker state right full width byte. So if we're in the state, if we've got to here and we're in the first command byte state and we haven't gone in, we haven't passed through the signal byte and received another command byte to say we're in the second state, then we're saying actually that command byte is actually representing a double. There's going to be a double U8 on its way, or it's going to be a full width byte on its way. So we just need to, another one is on its way. So we push the byte that we've currently got, that's the first of two, and then we were waiting for the second one to come by. And of course we need to go OK, meatpack, waiting for the next byte, and dereference that. There we go, dereference that. So yeah, we've got these 2 bytes coming in, and one we've already got, so we'll just push it in. Then we need to wait for the next one to arrive, and we'll push that onto as well. And that's where we get to the next stage here, the full width byte state. So yeah, we are now waiting. We know that we're there, so we just need to do in the full width state. Okay, we've passed that, so we can go back into unpacker enabled state, like the default enabled state. And after that, we'll push the byte, knowing that it's a full width character, into the buffer. Oops. And we should get OK. Meatpack result waiting for next byte. Oops, we don't need that semicolon there. So the why we're not, we're not checking for new lines here at all, because of course the new line should be already if we're in meatpack mode and we're doing this unpacking, they should only exist as U4s and be represented when we unpack them. So they should never be in the U8 full width mode. These are all other characters. We shouldn't be expecting a new line and to return a new line at any of these stages. And now we're on to the last stage of back in the left width byte. So this is the one that's got that little trick where we've in the buffer we've added the flag, so the flag character in there as a kind of temporary variable, and now we need to go back and find that and position this full width character in its proper location in the G-code. So first we're going to just go self.state back into unpacker state enabled, as we've now handled this state. We want to go self.inner, self.position -2. So we know that byte should be a couple of steps back from where we were, and so we just do -2, insert the byte into that position, and we just want to do self.inner, self.position -1. So the last thing we want to do is just do a double check whether this one is a new line character. If so, of course, we're going to want to clear our state once we return it, but we want to return a new line here. So okay, meatpack line and self.return slice, and otherwise we need to do okay meatpack waiting for next byte. And oh, I haven't put the if here. There we go. Oh, now even more. Remove the semicolons. Oh, there we go. Right, so full width mode, we know there's a position in the buffer that we need to insert this byte into, so that's what this line 128 does. Set into there. We then check that the the byte at the end of this buffer currently in our line of G code is not a new line character. If it is, we will want to clear the inner on our next round through and then return the slice of that line to the user. Deal with however they want. They've got a whole line of G code to handle. If not, then we return waiting for next byte. And that is the entirety of the Unpacker struct. So that's in essence all. Oh, let's just remove that up. This, if you go and look on GitHub and the actual crate repository, this is pretty much like for what's there now. I'm sure it's going to be evolved a bit more. We also have a couple of nice little lock additions. So we've got a feature flag. So if you do happen to have a lock available to you, you are working in a stud environment or you're using an allocator, we've got a couple of nice utility functions that just wrap around the Unpacker and Packer. And then you can feed a slicer, a U8 slice, and it will then do that byte by byte unpacking for you. We've also got a command line interface to pack and unpack G-code. So hopefully this was useful. Hopefully it's going to be useful to me when I look back if I need to fix anything or update the package. And I hope to see you in the next one.